start that? Yeah, okay. So these are two terms that are not, you've never seen really until you got to chemistry, and they're more related to a way. Yeah. Yeah, we rock. Seal it up and zip it up.
I didn't get them both.
Bye. Okay, so whenever we're talking about properties in chemistry, you can name off chemical properties, physical properties, all kinds of properties, but they're really categorized into two broader categories that relate to if it is dependent upon the matter that is present in that sample. So I'm going to start with extrinsic, okay? Extrinsic or extensive properties just basically mean that the amount, so the matter, let me actually use this, the amount of matter is going to be a part of why the property is what it is, okay? So for example, weight, if you have a lot of the matter, the weight goes up. If you have a small amount of the matter, the weight goes down. So the property varies based on amount is like kind of the most brief way you can say extrinsic or extensive property. So if you know that it's going to vary if you have more or less of the matter, then it's going to be considered an extrinsic property. So opposite of that would be a property that doesn't matter if you have 1 gram of the substance or a billion, bajillion, cajillion grams of it, right? It's always going to be the same property. The numerical value of it doesn't change, or like the description of it doesn't change, for example. So it doesn't matter how many grams of water I have, what's the melting point of water? Say again? Okay, let's go with what's the freezing point of water? 0 degrees Celsius. Okay, the freezing point of water is 0 degrees Celsius. That's also the melting point of water because they're just opposites in the way they go. So solid to liquid would be melting, and liquid to solid would be freezing. So the point is the same though, and it doesn't matter if I have a small bowl of water I'm freezing or a lake I'm freezing. It's the same number. Same thing with density. It's always a ratio of grams per milliliter. These two are some that we're going to talk about later, but they're more like the specific gravity is going to be based off kind of the density. It's like how much, based off this viscosity, how much stuff is in a certain volume, and it has another kind of property that goes along with it that's more applicable in like food manufacturing. Specific heat capacity has units of joules per gram degree C, and they're a ratio, joules per gram degree C, and it doesn't matter how much you have of the substance, it's always the same number. So inherently, the amount of matter doesn't matter. It's just an inherent characteristic. Can you compare and contrast those verbally if you had to on your test? Yeah? Okay. So there are, I'll go ahead and tell you guys now. There are, I don't remember, I think it's 8 dimensional analysis problems where you have to show your conversions using metric conversions. It might be like a minute to second conversion, so not metric, how to convert minutes to seconds. And word problems. So let's say there's 2 prefix ones, 3 complex ones. These are estimates, they might be slightly off because I don't have this right in front of me. And then 2 word problems. And the word problems, the hardest part about that is just finding the 3 pieces, right? The given, the question, and the conversion factors. So that's your free response part of that. There's 8-dimensional analysis problems. There is there are 2 descriptions. Compare and contrast questions, where I might give you 2 things to compare and contrast. When I say compare, I'm talking similarities. When I say contrast, we're talking differences, right? So from everything we've learned, what are some things that you might be asked to compare and contrast? Precision and accuracy. What else? Yeah. Chemical and physical properties or chemical and physical changes. Pure substances and mixtures, intensive and extrinsic. So I've got a couple of things I could go from, but I'm going to give you 2, and you're going to compare and contrast those. You have to do a rounding and sig fig based question. That's all in free response. And the multiple choice is more kind of like your problem sets where you're noting if something's a mixture, homogeneous mixture, heterogeneous mixture, pure substance, some stuff about scientific method, Lavoisier, So the scientist estimating or counting sig figs from a given quantity. I'll have to look at the multiple choice again. That's all I can remember from multiple choice off the top of my head. And our test is Friday, like we've got another day here. 2 days. Today's Wednesday. It's Wednesday. Okay. So let's talk about problem set 2 real fast. Okay. If you have a separate color, pull out a separate color. Let's talk about these, and then we're going to be done, and we'll move on to notes, and then we will move on to our lab. I'm actually going to start with number 5 because that was the one that a lot of us had some issues with. Number 5. And we're going to talk a lot more about this in terms of the law of conservation in our notes we're going to do soon. I just want to dissect this problem with you first. I can see that I have hydrogen and oxygen coming together to yield water. So which of these are the reactants? Nicole. Good. So everything on the left side of the yield symbol are the reactants, and everything on the right side of the yield symbol are products, right? So we kind of know how to look at an equation and determine that. But the law of conservation of matter just states that whatever matter you have in the beginning, you have at the end, because matter is neither created nor destroyed. So you can see, like, if you balance it, how many hydrogens are here? 2 times the subscript of 2 would give me how many? 4 atoms of hydrogen. How many oxygens here? 2, because there's a subscript of 2 there. So there's 4 H's and there's 2 O's. In the end, how many H's are there here? 4 hydrogens. And see, there's a 1 on the outside, but that 2 actually is like foiling out, it's distributing. So the 2 times the 1 gives me how many oxygens? 2 oxygens. Okay. You guys have a periodic table close by. It should be like a salmon or orange color. I just want to point out some stuff on the periodic table. We'll use it more on our next unit, but I'm just going to give you the brief of it right now. Where find hydrogen is in the upper right-hand corner. I'm sorry, upper left-hand corner. Find hydrogen and tell me what its mass is. 1.008, right? I'm just going to round that to 1 just for easiness sake. So if I have 4 hydrogens, what's their total mass? 4 grams, right? Okay, so this is my hypothetical problem. I'll get back down to the C in just a second. Look for oxygen. It's in the upper right-hand corner. Or oxygen. What's its mass? 16.00 grams, right? So I have 2 oxygens. How much is that total? 32 grams. So collectively, the 4 H's and the 2 oxygens together weigh what? 36 grams. So if I just had that, if I had 36 grams over here, because I just look at the matter I have and the mass that it weighs, I add it up. What's the mass over here? Same thing, why? Because it has the same numbers of atoms of everything, right? So the matter is conserved. There's 4 H's, there's 4 H's, there's 2 O's, there's 2 O's. Matter is conserved. So if matter is conserved, its mass is also conserved. Because matter and mass are like inherent, they're just directly related. So there should be 36 grams on this side. So if I didn't tell you, let's say I told you this was unknown element, question mark. And I told you this was 4 grams and you didn't know this, but I told you the final mass of all of this over here was 36. Could you figure out what the mass of the missing piece was? How? Well, hold on. First, you would do what? Find the difference. I heard somebody say subtract. You would do 36 grams on this side and 4 grams on this side plus x, because you don't know what that is. So you first solve for x to be what? 32 grams, and then you could divide it by 2 to just find the mass of or unknown, what we're calling oxygen. In this case, if I really wanted to go that far. But for our sake, I just want you to see that mass is conserved. So in this example, part C, if that much oxygen is produced, this much oxygen is used to produce this much water, how much of the hydrogen would have had to react? So the oxygen is on the reactant side, so 26.4 grams, and the question is about hydrogen, correct? So it's asking for X, so I'm going to call that hydrogen right there. And I'm not even considering the 2, it's just saying how much hydrogen total do I have. That's going to yield 79.24 grams of water. that much water is total product mass. So then I just need to solve for x. I need to subtract to figure out how much hydrogen's there. So how much is that, guys? 50 what? 8,4. And are we good on sig figs there? Why? Because when we're looking at sig figs, we're considering what when we subtract. Say again? Decimals, right? And the decimals are 2 decimals, so we're left with 2 decimals. So that's how you can figure out a mathematical problem based off that. But I want you to be able to do with conceptual stuff too. Like if I asked for, what would be the missing piece, you could find oxygen and so forth. So, yes, it stays, okay. Let's look at, so as we went over chemical and physical properties a lot yesterday, so I'm going to stick with some of the other stuff we've not done recently. Tell me I want you to chant with me here, okay? Number 1A, what'd you guys put? Okay, pure substance compound, good. So, because you have to classify it as pure substance and then a secondary category compound. Next, mixture, homo, okay. Club soda, this one might be a little different, but everybody should have gotten mixture for sure. And if you put homogeneous, because if you stand back from the club soda, you can see the bubbles and the water are all kind of evenly distributed. If things are evenly distributed, even though you can see the pieces of it, I call that uniform, so I call it homo. But it depends. Like, I'm pretty flexible on that one. Sometimes it's up to your opinion. D? Pure substance. Pure substance elements. Steel. There's another name for a mixture for this one. I just want to know if we know what it is. Alloy. Good. Number 4. So number 4 on there asks for, like, what's a mixture of two metals, or what's the definition of an alloy? It's a mixture of two metals. Steel is made up. Did anybody look that up? What it's made up of? Iron and carbon. Good. Whoever said that. So steel is a mixture of metals, and so it is a mixture, and you guys do say it's homo. Homo because it looks the same throughout. Steam. I'm going over here to H. Steam. Pure substance. It is a compound. What is a compound that's in steam? H2O, right? And if it's a formula H2O, you can see the two elements that are combined in a compound form. Let's do carbon dioxide over here, F. Pure substance compound, good. Okay, and the other ones I think we're good with, but I want you guys to ask any questions you need to. Anything you're not clear on? Yeah.
What was G?
G, chlorine. Chlorine gas is a pure substance, and it's an element. There it is. Cl is the elemental form or symbol for chlorine from your periodic table. Okay, so pure substance element. Another question over here? Okay, let's do some notes real fast on law of conservation of matter. And then we're jumping into the lab. And some of this might not be a lot that you need to write down. I want you to write down what you feel like you need to write down. So don't feel like you have to write down everything just because it's up there. And so out of everything we're going to just talk about briefly with the law of conservation of mass, this first statement is really the most important conceptual part of it. So read it and write down what you need to. And I'll go through some examples with you in a second. So whenever we all kind of know that matter is neither created nor destroyed. We've talked about that probably 3 times today. But what's happening to it is that it's rearranging where it's located on the compound or in the compound. It might even break off and form a free element all by itself. So it just changes form, and kind of our terms, we mean that it's just rearranged. But in order to do this, you have to break compound bonds. CMPD is compound. And that usually is going to be like more of an endothermic process where we have to break the bonds in order to do some work. That might be putting energy in, such as like catching things on fire. We have to force it to do some break the bonds so they free up so they can rearrange. And would that be considered a chemical change or a physical change? Chemical change, because we actually are making new substances. And if we're making new substances, like in this example, we're taking reactants, we're making products, that will be a chemical change. And what are some evidences of chemical changes? What do you see that says, hey, I'm a chemical change? Bubbles, what's the educated version of that? Gas evolution. What do you call when something gets hot? So you can either say temperature change, or you can go fancy and go heat evolution. Anytime it says evolution, it just means made. What else? What was the white stuff you saw in your test tube yesterday? Precipitate, right. Heat evolution, precipitate formation, gas evolution. What else? Unexpected color change, meaning we're making a new compound with a totally new property of color. So you got all these things that you can use to indicate if something's a chemical change. So you can see, for example, in part, in this third example down here, A and B are together, C is separate. These are just generic elements, of course. And as we do the rearrangement, A and C are now together and B is separate. So that just is a pictorial version of a chemical reaction. Thumbs up, you good here? Okay, cool. So this is familiar to you, yes? Yay. Okay, so I used to make my biology students do this dance. It's called the sun, and the rain. And the CO2 makes food and oxygen for me and you. That's how you remember photosynthesis. And then my AP class did it for one of their AP Chem class did it because they were like, we want to do biology dance. Anyway. So this is our photosynthesis process. You can see the conservation of matter if you count up the compound or the atoms. So can we quickly just verify the conservation of matter here? So how many carbons are on the reactant side? 6. There's an imaginary 1 after the carbon, and that 6 times 1 says I have 6 carbons. You see that? Yes. Okay. How many how many hydrogens on the reactant side? 12. 6 times 2 there gives us 12 hydrogens. And then how many oxygens total here? Good, I heard it. We said 6 times 2, which is 12, plus the 6 times 1 on this side. So that's 18 oxygens. So I, in the future, will not give you these coefficients, and we are going to be balancing by ourselves, because I don't have to give you the coefficients. You can figure it out based on the way that you need to kind of fit the puzzle together here. And then verify that matter is conserved. How many carbons on the product side? Good. There's a 6 right there. There's a coefficient of 1. 1 times 6 is 6 carbons. How many hydrogens? 12. And how many oxygens? So 6 times 2 over here is 12, plus the 6 right here gives me 18 oxygens. So the law of conservation of matter is represented by making a balanced chemical equation. So BCE is what we call that, a balanced chemical equation. And that's just how scientists depict that the law of conservation of matter or mass is being exhibited in that reaction. And that's what we call a balanced chemical equation right there. Most of us are familiar with that though. So BCE is balanced chemical equation. And then we just did that. These are just some other examples of chemical reactions that you will soon be exposed to. If it's reacting with oxygen, what do we say about that? What kind of reaction is that? Combustion, right. So you should remember that reacting with oxygen means combustion. And these other ones, these are some examples that we talk about in our chemical changes, part of our homework. Tarnishing of silver and rusting of iron. It's just a process that occurs with that individual element, the metal, and usually a gas. So that gas is oxygen that's reacting with, and this is actually sulfur gas. And sulfur gas, you guys know what sulfur smells like? It's rotten eggs. It smells gross. You ever go through, is it Cantor, like going towards the mountains? It smells awful. They have like a sulfur plant or something. I just call it a rotten egg plant because I don't know if they're making paper mill or something like that. So I'll do these later with you guys. We're doing our lab. Okay? Fluffy stick for lab. you are going to be a scientist and you're going to try your best to either confirm or disconfirm the law of conservation of matter or mass based off measures. So you're collecting all that data, you're going to analyze your data and say, does this method of experimentation confirm the law of conservation of mass? Yes or no. You're doing 3 experiments in one. You have one where you'll be doing it in a beaker. The beaker that it calls for in the lab says it says it should be a 600 milliliter one. It's okay to be like a 250, a 200, because our scales they max out at 200 or 300 grams, so that was going to be too heavy. So I would use something like a 200 to 250 milliliter beaker for that first part of the reaction. The other ones are pretty self-explanatory. They say use a bottle, contain the reaction, close off the lid, and then there's another one where you have to be kind of creative in how you set it up. Okay, so there you have all the materials in your little buckets and in your cabinets underneath. Afterwards, just make sure that if you need some help figuring out where the chemicals goes, let me know. But wash everything out normally. The question on the bottom to ask about percent error, you can read this when you get there, but whenever you're comparing, you're going to be comparing your initial masses with your final masses. And if the law of conservation of mass is occurring, what should be true about those 2 masses? They should be the same, right? And if they're not, we have error. And that's what I'm actually asking for you to measure, is the error of the masses, not like true percent error in this case. After that, I'll kind of point you in the direction where you can start your periodic table assignment, but this is going to be using a blank PTOE from your first day folder, and I'll show you where it is on my website. I'll pull it up on the board, and you guys have the Chromebooks to start that, okay? Okay, lab groups, let's go. Goggles, goggles, goggles.